Hi guys, welcome to the continuation of our lectures on quantum field theory, and this is the second part of chapter 5 on Klein-Gordon equation, the scalar fields. And along with these lectures, please read the books of Michio Kaku, Quantum Field Theory, Mandel and Shaw, Quantum Field Theory, and Gross's Relativistic Quantum Mechanics and Field Theory. So in this lecture, we will start with an example. So here you have, suppose that you have a real scalar field given by this one, this phi, a function of space-time. And we will compute the equal time commutator here. But there's a condition that your XO and YO are equal. So before we will be able to compute the commutator, let's calculate first the momentum, which is just equal to the partial derivative of phi with respect to the the time coordinate x0. So in this case, we're just having a phi that's for a free particle. Free particle solution. So you have this commutator here. This is just, of course, the difference between the products, the interchange products. Now let's look at the momentum. So this is just the derivative of phi with respect to x0, and so we're just taking the derivative with respect to x0 here, and so with that you will be able to get a factor p0 in the numerator, and that will just cancel with the p0 in the denominator, so that you will have this factor in the pi expression. So looking at the product, of course these are what you call the phase factors, and this one here are the x terms and the y terms, different times. So if you get the product, expand the product, you just do multiply algebraically, but be careful about the ordering of the commutator, of the operators, because they're not ordinary numbers. So in this case, you have phi pi, or phi x pi y, is given by this, and of course the second term is given by this, and then you will now have to subtract this one from this one to get the commutator. And by the way, they obey similar commutation relation to the creation and annihilation operators used in simple harmonic oscillator. And in the continuous case, you will have the Kronecker delta instead of the usual I'm sorry, it's not the Kronecker delta, but the continuous delta function here. So it's not a discrete Kronecker delta. So by the way, the commutation relation between two annihilation operators is 0, and for two creation operators is also 0. You only have non-zero for the commutation relation between the annihilation and the creation operator. So taking a difference of the first term computed for phi x, pi y, and the first term computed for pi y, phi x, this one here, so basically we're talking about the first term. Of course, this is just, we won't bother ourselves with these factors, but the first term here minus this, the first term here. So, and of course this is of course similar to, the solution will just be similar for these terms also. And now we have this one for the first term, and since they follow the simple harmonic simple harmonic oscillator commutation relation, so this one is equal to 0, and because this one is equal to 0, and then that is also true for the last term, so the fourth terms. Now we consider the second term in each expression. So take the difference between this and this one. By the way, let me just also clarify that this is actually a minus sign. Yeah. So let's continue. So the second term will be just this one, and it will give us, since you have this as your factor in the calculation, and this is just equal to the continuous delta function of p minus p prime, so you have this one. And use the fact that the Dirac delta function has this property, and of course there's a condition that you have to also consider to get rid of the time component. And so applying the same procedure to the third terms in each expression will also give you a result which is equal to this. So finally, our commutation relation would have to be by the way, this is just equal to this one. And so of course the result is using this particular property of the Dirac delta function, so that your commutation relation is equal to this one here. But we also know that the Dirac delta function is also defined by this one, so that we'll be able to get and also, by the way, before that, the continuous Dirac delta function here this is also true, so that your commutation relation will actually just give you this one between phi and pi. Okay, that's it. So I hope you can remember that result. So we'll now go to the states in quantum field theory. Now, states in quantum field theory. Now that we know how to write down the scalar field in terms of creation and annihilation operators, we are now ready to see how the operators act on the states of the field. And recall the idea of how they act by analogy with the simple harmonic oscillator we discussed in the first part of this lecture. Now let's consider the simplest case, the state of the lowest energy, or the ground state, or the vacuum state in quantum field theory, which is denoted by this one, a state of zero particle. That means that there's no particle there in quantum field theory. And the annihilation operator would be able to destroy that field. Actually, there's no particle there, but the field is still there. And if you apply an annihilation operator, it becomes zero. It will destroy the field. The creation and annihilation operators enter the field by the Fourier expansion and have been labeled by the momentum p, or wave number k. States can be denoted by momentum as well states can be denoted by momentum as well. So can be step up from a vacuum state to a k state. This means that from a vacuum state you can create a particle with momentum k if you apply a one particle state with momentum k. But if you do multiple creation operators of different k modes, say for example you create two particles, so you can create for this one and for this one, so you have two particles with k1 and momentum k2. And for n particle states, you'll be able to create them by applying creation operators multiple times, or say n times. But in this case, you have particles which have momentums that are different, k1, k2 until kn. So each creation operator A adjoint ki creates a single particle with momentum hki and energy omega ki. By the way, in this particular notation, we have h here, and it's just for clarity of unit. So anyway, here you have omega equal to the momentums, the square root of momentum plus the mass. So an annihilation operator A ki destroys a particle with the said momentum and energy. So let's look at the positive and negative frequencies, the composition of the field. And the field can be composed into two parts, a positive frequency part and a negative frequency part. The positive frequency part consists of annihilation operators, and you have this part, and of course the negative frequency part, which is the field composed of creation operators. So actually you have your phi as a combination of your annihilation operator, positive frequency and negative frequency. Therefore, since if you apply annihilation operator to the field 0 gives you 0, the positive frequency part of the field annihilates the vacuum in this case. So you have a field that is destroyed. A state where there is 0 particles. You annihilate that and it just goes to nothing. And the negative energy, negative frequency part, creates particles. So in this case, you will have this. So you just create a particle out of this one. So you create one particle with momentum k. So this is now your negative frequency part of your field operator, and this will give this is the result of that. So we'll now go to, so I hope you are already familiarized how to operate your phi on this of the state. So number operators. A number operator can be constructed from the creation and annihilation operators. This time this applies to creation and annihilation of particles, wherein the harmonic oscillator it applies to energy, increase or decrease of energy state. So in this case, a number operator can be constructed from a adjoint and a. The eigenvalues of the number operators are called occupation numbers, and these are integers 0 to n, or say infinity if it's permitted. And that gives the number of particles there are of momentum k for a given state. So say for example this one, then it's just equivalent to this. So that is a state where it consists of n particles with a single particle momentum k1, k2, and a particle with momentum k3, and so on. However, there are states where there are multiple particles with the same momentum. Suppose that there are two particles with momentum k1 and a single particle with momentum k2. As the state can be written as this one here. So there are three particles, but two of them are of the same momentum and the other one is another. In this case, you have square root of 2 as a normalization factor with two particles with the same momentum. So in this case, you have your nk for momentum k1 is 2. So in general, from the vacuum state, if you have um, if you have two particle, I mean, not really, if you have um, two momentum, but however many particle system state, but there are only two momentum in that state, then you will have this one. But in general, you would actually have this one. So it is, as it is written, the number operator nk, which is just a adjoint a k, is actually a density giving the number of density of particles in a given state. So to get the total number of particles integrate over all the states in a momentum space, and this is done by integrating over momentum space a adjoint a. So let's now proceed with example 6.3. Find nk prime. So we have, of course, this is a definition of creation of a particle with momentum k prime, and this is the commutation relation of a and a prime. I mean ak and a adjoint k prime. So this one, you can actually write k prime as this part here, and then using the commutation relation you can write this part as this one. So you can so anyway, when you have this one, that is just equal to 0, because it applies to this and this one, and applying that will just give you 0, so that you will just have this. And so this will just commute with this one, and so you will have this. Therefore, that is just equal to so now you have your n equal to this. Now to find n is just given by this one, so that your n and operating on k prime, we'll just have this one. But this one, this part is already delta, which is this one, and so you have k prime, the state k prime, or a single particle k prime, and therefore your n here, which is the eigenvalue for the n operator, that's just equal to 1. How do you normalize a state? So for the vacuum, the normalization is just equal to 1. And let's now compute the normalization of state k by considering the inner product here. I hope the solution is just easy to follow. So starting from this line, you can use the commutation relation of A and A adjoint, and so eventually you will get the normalization of the two states will just be like that. One of the basic characteristics of Bose-Einstein statistics is that the particles can interchange without changing sign. And if you would also see, this one is just that one, and but this one here commutes with itself, so this state can also be written as like that one. And as you can see, you have changed the momentum, the order of momentum of the two particles, but there is no change in sign, and so therefore you're dealing with bosons instead of fermions, because had it fermion, then the change of positions of two momentum would have negative sign, but there's no change, so therefore it's bosons, not fermions. So scalar particles are boson particles. We can also get the energy and momentum of a particle by applying of a state by applying the Hamiltonian and the momentum operator. So here we have for an operator in that form, and using this one, the number operator, it can be shown that the Hamiltonian operator is this, and the momentum, the Hamiltonian is that one, and the operator is just, the momentum in the field is just this one. For the real scalar field, find the energy of the vacuum here. The solution to this example is the famous infinite energy of the vacuum, which may or may not be a problem depending on the point of view. So to find the energy of the vacuum, we compute by applying the Hamiltonian operator in between the two vacuum states. And know that you have to substitute h with the expression uh, integral with respect to momentum's case omega k times nk plus 1/2. So I think that it's the solution is very clear, so that you will have this as a result. So the solution is reminiscent of the energy of the harmonic oscillator, and in that case the energy of the ground state is 1/2 h bar omega. But look at the integral of the momentum space. The momentum space could go to infinity, this one. However, that result can be ignored depending on your point of view. Usually only the energy differences are measured. So energy is measured relative to the ground state, and this term falls out. So in the end it can be said that the energy is 0. Now if we just simply subtract the infinity and say the theory is being renormalized, this trick works. But think about the fact that mathematical insertion was done to make the theory work. Perhaps this is an indicator that things are not quite right. So you can actually change the Hamiltonian into this one, which is a renormalized Hamiltonian constructed by subtracting off the term that gives rise to the infinite energy, so that dk, integral with respect to momentum space Wn omega n would just be equal to this. So now find the energy of the state K using the renormalized Hamiltonian. So with that, your renormalized Hamiltonian gives you this, which is now without the infinity that we had earlier. Normal and time ordered products in QFT, it is desirable to write expressions in a way such that all creation operators are to the left of all annihilation operators, like this one. So the normal ordering of a scalar field can be written down using the positive and negative frequency parts. Look at the normal ordering notation. You have columns on both sides of the expression. So if you recall, say this one is your positive frequency state and negative frequency state, and the normal ordering puts creation and operators to the left, so expect the normal ordered field to have negative frequency parts to the left and positive frequency components to the right. The negative frequency parts are on the left of the positive frequency parts here, and so your normal ordering here would give you this. In other words, if you apply this to a particle state or a state, not really a particle state, but a state, um, you have to create particle first before you can destroy the particles. So and that's the normal ordering. Now there's also a time ordered product, which is is a mathematical representation of the physical fact that a particle has to be created before it gets destroyed. Yeah, that's why the normal ordering. So time ordering is accomplished by using the time operator, which acts on the product, this one. You have phi t1 and psi t2. The time ordering product is that you have this one if t1 is greater than t2, and this one also if t2 is greater than t1. Remember the fields are operators. Operator act in a right to left order, so a product of operators A B acts on the state psi in such a way that B acts on the first B acts on the state first, and then you have A acting subsequently on the results of B psi. Therefore, if T1 is greater than T2, which means that T1 is later in time, psi 2 acts on the state first, followed by the action of phi T1, and the order is reversed if your T1 is less than T2. So that's time ordering. That's the time ordering. Quantizing complex scalar field. This is a good step forward because the complex scalar field represents particles with charge q and antiparticles with charge negative q, and we'll see how antiparticles can be represented in quantum field theory here. Dealing with antiparticles, the field is expanded in terms of positive frequency modes, annihilation operators for particles, and negative frequency modes, creation operators for antiparticles. And in this, it is common to use the creation and annihilation operators for this one, for A for particles, and we represent B or denote B to represent the creation and annihilation operators for antiparticles. Hence, A adjoint K creates a particle momentum hk and energy omega k, while B adjoint K creates an antiparticle momentum hk and energy omega k. So to write the field operator, sum of positive frequency parts for particles together with negative frequency parts for antiparticles. So we have this as our field operator now. And of course the adjoint field is given by this one. And the commutation relation still follows this one. In this case, there are two conjugate momenta corresponding to the field and its adjoint. In the case of the complex scalar fields, for example, you have this, and so you will have this one. For charged complex field, there are two number operators. The first is the familiar number operator that corresponds to the number of particles, and the second is the number operator that represents the number of antiparticles. Here and this one. The total energy in the field is expressed as the energy of the particles added to the energy of the antiparticles. Here. Notice that the energy density is the number density of particles added to the number density of antiparticles, multiplied of course by the energy. And you can get the total energy by integrating over all modes of the field. And the total momentum is the momentum due to the particles added to the momentum due to the antiparticles. And so you will have the total momentum operator to be that expression. Of course, you have their particles and antiparticle parts. By the way, a complex field corresponds to a charged field for particles and antiparticles having opposite charge. The total charge can actually be found by subtracting the charge due to particles from the charge due to charge due to the antiparticles from the charge due to particles, and the charge operator is written in this expression, and you will have just the number of particles minus the number of antiparticles. So finally, the field and the conjugate momenta satisfy a series of commutation relations. We're again considering equal time relations such that XO and YO are the same. Then your commutation relation for phi x, pi y. This is field and momentum commutation relation for both. For the combination of particles and antiparticles is just that one. This is the same as what we had. All the equal time commutators vanish, leaving the column which is not an equal time commutator. This one here. Of course, at equal time, this is just equal to 0. By the way, this commutator is what we call the propagator, and this propagator will be discussed later on, maybe in the next two chapters, after the next two chapters. So let's look at the summary. The Klein-Gordon equation KGE results from a straightforward substitution of the quantum mechanical operators for energy and the momentum into the Einstein's relation for the energy, momentum, and mass relationship from special relativity. And this leads to the inconsistencies like negative probabilities and negative energy states. And these were resolved by reinterpreting the equation. Rather than viewing it as a single particle wave equation, instead apply to a field that includes creation and annihilation operators similar to the harmonic oscillator in quantum mechanics. But there is one difference, since the creation and annihilation operators now create and destroy particles rather than changing the energy levels of an individual particle as it was in harmonic oscillators in quantum mechanics. You will be dealing with particles and antiparticles instead of just energy. So you have some quiz here, but you don't have to answer that. I mean, in your free time you can do these things. So that's it, folks, for this lecture. I hope you learned something, and hopefully in our Q&A you'll be able to ask questions.